In this video, I'm going to talk about how Lipschitz continuity is related to the convergence of Fourier series to itself. So, let's state our theorem. Our theorem states that if f is a 2-pi periodic function which is integrable on the interval negative pi to pi, and we suppose that f is a Lipschitz continuous function at x which lies inside negative pi to pi, then we have the partial sum of the Fourier series of f tends to fx as n tends to infinity, which means that the Fourier series converges to f. So, how can we prove so? Well, first of all, we recall that I2 equal to the integral from negative pi to pi of chi b d n z times fz plus x minus fx, which tends to 0 as n tends to infinity. And by the definition of limit, it means that for all epsilon greater than 0, there exists an n1 such that the absolute value of I2 is more than epsilon over 2 as n greater than or equal to n1. So this is not the issue we want to deal with. We want to deal with I1. So if we do the same estimate as before, we know that the absolute value of I1 should be smaller than or equal to the 1, which putting the absolute value inside the integral sign. And let's start using our assumption. Our assumption said that by the Lipschitz continuity of f, we know that there exists a delta 1 such that the absolute value of fx plus z minus fx is more than or equal to L times x plus z minus x, which is essentially equal to L times absolute value of z, as the absolute value of z is smaller than delta 1. Also, we know that as z tends to 0, z over 2 over sine z over 2 tends to 1. So, we know that for all epsilon greater than 0, there exists an delta 2 greater than 0 such that the absolute value of z over 2 over sine z over 2 minus 1 should be smaller than delta, as the absolute value of z is smaller than delta 2. As this statement is true for all epsilon greater than 0, we can freely choose our epsilon. And now I would like to choose epsilon equal to 1 and apply the triangle inequality. We get that the absolute value of z over 2 over sine z over 2 is smaller than 2, as absolute value of z is smaller than delta 2. If we choose the delta smaller than the minimum of delta 1 and delta 2, we get both inequality in the previous page, as the absolute value of z is smaller than delta. So the absolute value of L1 should be smaller than or equal to the expression in the previous page. And if we multiply and divide an absolute z, then we get this expression. And remember that from the first inequality, we know that the first expression here is more than L, while the second expression here is more than 4. So we know that it is more than or equal to the integral from negative delta up to delta of 4L over 2 pi dz. And if we integrate this thing explicitly, we get that it is equal to 4L over pi times delta. So we want L1 as small as possible, so we can choose this delta as small as possible. So if our delta 1 and delta 2 are not small enough, we can restrict our delta smaller than pi over 4L times epsilon over 2. So we know that the absolute value of L1 should be smaller than 4L delta over pi, and this is smaller than epsilon over 2. And remember that the difference between Sn fx and fx is equal to L1 plus L2. So apply the triangle inequality, we can get that it is smaller than or equal to the absolute value of L1 plus the absolute value of L2, which is more than epsilon over 2 plus epsilon over 2, which is equal to epsilon, as n greater than or equal to n1. And by definition of the convergence of sequence, Sn fx indeed will converge to fx. And indeed we can further generalize our previous theorem. Let f be a 2-pi periodic function which is integrable on the interval negative pi up to pi. And suppose that x is a point inside the interval negative pi to pi such that the fx plus, which is the right hand limit of fy, and fx minus, which is the left hand limit of fxy, exist. And we suppose that there exists delta and L such that the absolute value of fy minus fx plus is more than or equal to L times y minus x for all y which satisfy the inequality 0 is smaller than y minus x is smaller than delta. And another inequality is that fy minus fx minus absolute value should be smaller than or equal to L times x minus y for all y which satisfy the inequality 0 smaller than x minus y smaller than delta. Then we know that the Fourier series of f at x will tend to the average of the left hand and the right hand limits. And I will leave it as an exercise for you, because the proof here is essentially the same as the previous theorem. So this is the end of the video about the relationship between Lipschitz continuity and the convergence of Fourier series to the function itself. So see you in the next video.